Hello and welcome to York Universe, the Astronomy and Astrophysics radio podcast, written and presented by the students, faculty, alumni, and friends of York University. You'll now find us wherever podcasts are distributed. I'm Sana Withers, I'll be one of your hosts this evening, and I'm joined tonight by Professor Mary Helen Armour. We're broadcasting live from the Allan Carswell Observatory, located at York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday night at 9 p.m. local Toronto time, or Tuesday morning at 1 a.m. Universal Time. We broadcast live on our YouTube page at the handle York U Observatory and run in concert with our online public viewing program run by the Observatory team. To navigate to the live show or to find out more, and check out our website at yorku.ca/science/observatory and follow the links to the online public viewing. For any questions or comments you have on any of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can also always connect with us on Instagram with the handle at YorkU Observatory and on Facebook at Allan I. Carswell Obs. All of our programs are free, but if you would like to make a donation, please see our website at yorku.ca/science/observatory. We will be monitoring the chat rooms for questions and to post content. But unfortunately, we won't be doing any live observing tonight because the weather the past couple days has been really terrible. So we're just going to take a look at some of our archival images, many of which were taken by our 1 meter and 40 centimeter telescopes that our online public viewing team will be posting online. Mary Helen, how are you?
Oh, pretty good. Sorry, just have to figure out where the unmute button was there.
Yeah.
I actually was out just before the show and I could see a star or two while I was letting my poor dog out quickly, but
Oh.
I don't think it'll last long.
No, it looks like there's a game happening at the Lions Stadium tonight also. So the stadium lights are on full blast and not really a good night for observing either way.
Yeah, it's poor weather and this does not look like a very good week for much observing at all. So,
Lots of rain, high humidity, kind of, muggy sort
yeah.
of terribleness. Um, but I mean, it's going to start getting cold soon, so I guess this is one of the last weeks we're going to have to put up with the muggy weather.
Yeah.
Yeah. But we have a very sort of solar system planet themed show for tonight. And you are first up with the equinox.
Yes, as I texted my husband earlier today, happy equinox. It occurred about 2:17 p.m. at today, Eastern Daylight Time. From a seasonal point of view, we usually consider the fall equinox the official start of fall. Uh, but generally, there's not a drastic change in the weather around this time. It's just one of those timekeeping points we have. Now, the question popped up as somebody was asking me today, like, well, if it's the equinox, why, doesn't the sun rise at 7 and then set exactly at 7? And the truth of the matter is, although we call it the equinox, and it's pretty close to equal right now, what really defines the equinox is when the sun is sort of directly over the equator. And this has to do with how the Earth is aligned at this time of year, that it will appear to stand sort of directly over the equator. And that happened about 2:16 p.m. today, because otherwise, as the Earth goes around the sun, of course, it tilts. So where exactly it appears in the sky shifts back and forth. And how we define the equinox has to do more with where it is relative to Earth than actually the length of the day. Length of day is a little more complicated as to sort of how you get sort of equal day and equal night. Um, just because there's more factors that play into it. The Earth isn't perfectly round, Earth's orbit isn't perfectly circular. There's all kinds of things that kind of come into it. But that's why, it's usually not exactly uh, equally day and night. It gets that name because, of course, when people were first doing timekeeping, it would seem pretty close. Like if you didn't have extra timekeeping and you were just looking at sort of the equinox, you might think, okay, well, it's about the same length day, but it's going to be like that for a few days, really, either on either side of the equinox. This idea that people knew exactly when it was. It was actually probably fairly rare. You had to be a fairly sophisticated observer to do it. Certainly some groups like the Mayans and the Babylonians did, but for the most part, most groups knew, roughly within, a few days on either side, the day length was about the same. Same thing for the solstice when you had the longest day of the year or the shortest day of the year. It was roughly a time period of a few days. Um, but this is how they did timekeeping, right? If you don't have a clock, if you don't have a calendar, how do you keep time? You watch what the sun is doing. And in fact, York has a donor who has provided with the funds to build actually a really interesting sundial near the observatory, which should be happening in the next, at least should be starting in the next few months. And a sundial is, one of the earliest sort of solar observing instruments, but it also functions as a calendar. And this all ties into sort of when the equinox is and how we mark it and those kind of things. So,
Yeah, it's really interesting. One of the things that was a little bit mind-boggling to me when I started actually learning about astronomy and different ways of like timekeeping is just having a clock and always knowing what time it is really something that I felt like I took for granted almost. But yeah, everything used to be so much more complicated. Even doing things like measuring time of day, time of year was like it was a process.
yeah, and like it's not that we couldn't do it. It's just we did it totally different ways, right? But this is why sort of astronomy and astrology, I think, had so much power in a lot of societies because that's how you told time. That's how you could predict what was coming with the seasons and everything. So it really, although nowadays we go to, oh yeah, it was the equinox, big deal. If you go back to, especially because most societies were based on agriculture, you had to know when the seasons were about to change. Because obviously, if you're out there today, you might think it's still summer, and yet, in this part of the world, we can get snow as early as, mid to late October. So you had to know like what was happening. When is the right time to harvest the crops? When is the right time to plant the crops? Because weather alone is not really a great indicator of what the season is. And yet the equinoxes and the solstice are very, very predictable. So they used that quite a lot in order to, it was a survival thing. Like we kind of brush it off, oh yeah, whatever. But this is why they built the Stonehenges and so many other ancient monuments that have these alignments because, this was really important.
Yeah. Yeah, it's really cool. I'm looking forward to getting that sundial and actually being able to kind of show people the way sundials work. This should be a fun thing to have here.
Oh yeah, I mean, at its most simplest, any stick in the ground can function as a sundial. But
Yeah.
this one's going to be quite a bit more complex. I don't think I've actually seen the design yet, but it's going to be quite large, is my understanding.
Yeah. I've heard a little bit about it here and there recently, but I haven't actually seen any kind of designs or anything. But yeah, it'll be really nice to have by the observatory.
Yeah, and it's interesting because it kind of brings us back, I think, to a little bit of our history. And it doesn't matter where you are, all humans on some level or another use that kind of movement of the sun and tracking the movement of the sun to tell time. It varied a little depending on how far north you were, if you were closer to the equator. But, it distinctly was sort of the main timekeeping device for most early societies. So, yeah.
Yeah. Yeah, so that was an interesting sort of I guess more ancient this week in history slash news. The next one is bringing us forward in time to 2017, September 15th specifically, which was the end of the Cassini mission to Saturn. Now, Cassini, like I said, it's a mission to Saturn. It ended up orbiting Saturn for around 13 years in total. Was a completely revolutionary sort of satellite that really changed the way that astronomers understand Saturn, both the planet itself, but also the whole system in general. So the system of rings and its system of moons. So Cassini itself was a more NASA-led mission, but Cassini also had a little companion on board, which was the Huygens probe. The pair, Cassini and Huygens, launched in 1997, traveled to Saturn together until 2004 when they entered orbit around Saturn, which in itself was a major accomplishment because they were the first man-made objects to actually orbit Saturn. There had been a couple of visits to Saturn prior to this, but they were things like the Voyager 1 and 2 spacecraft that just did flybys of Saturn. So they got sort of quick peeks of the planet and then kept going. But one of the real benefits of having orbiters like Cassini is that you can actually really look at like the long-term variations in the planet. So how the storms on Saturn act over very long periods of time. Now, I mentioned the Huygens probe here because it was a really fantastic part of the Cassini mission. Huygens was actually led by the European Space Agency, and what it was designed to do was just to land on the moon Titan. Titan is a really weird and very, very interesting moon in the outer solar system. There's tons of those kind of weird, almost planet-like moons that exist in the outer solar system. But Titan specifically was chosen partly because it was just very hard to observe if you're not actually landing on the surface. It has a very thick atmosphere that's all made of methane, which makes it actually hard to observe the surface or impossible to observe the surface in visible light. So you really need this type of lander that will actually, pierce through the atmosphere and land on the surface of Titan to properly understand and properly observe this moon. And that's what the Huygens probe did in January of 2005. It detached from Cassini and landed on the surface of Titan. It took around 2.5 hours for it to descend from the top of the atmosphere all the way to the surface. I think it just had a big parachute that kind of gave it this really slow descent and gave it time to just take images and collect data of the surface of Titan as it was going through this descent. And it really revealed that Titan is this really crazy, I'm tempted to say almost Earth-like type of world, just because of the type of weather that it has. So Earth has these massive, lakes and oceans and weather systems that are all based off of water. And it turns out that Titan has a lot of the same stuff, except it's all methane. And that was one of the major results that came out of the Huygens probe, is that it kept discovering all of this very dynamic system and this very dynamic world on Titan, but it was very far away from the sun, so very cold. So you can't really get liquid water in those conditions. And instead, you just get this world made out of methane. Now, back to the Cassini mission itself. Even though the Huygens probe landed on Titan in January 2005 and ended its mission after that, Cassini kept going and it must have been hundreds of orbits around, potentially even thousands of orbits around Saturn, observing the planet, its rings, and its moons. So we could probably do a whole series of episodes dedicated to all of the cool stuff that Cassini discovered at Saturn. But I'm just going to kind of do a couple of highlights so that we don't spend the entire show talking about this. But in terms of observing Saturn itself, it observed a whole whack of extreme weather on Saturn in more detail than had ever been observed before. So these were things like observing lightning on Saturn for the first time. And it even produced the very first videos of lightning on a different planet while it was observing this lightning on Saturn. It also observed this weird hexagonal shaped storm on, I believe it's the North Pole of Saturn. It's actually really cool if you look up pictures of this. It is really a storm, a giant storm on the pole of Saturn that is shaped like a hexagon. There's a kind of funky, really interesting discovery right there. In terms of Saturn's rings, it also found a new ring of Saturn called the E ring. This is a very faint ring, so it's not easily observed through like ground-based telescopes, which is why Cassini had to go there to actually discover this E ring. And it also did a whole lot of observations of the way that the rings and the moons of Saturn can actually interact with each other. One of the really cool things it discovered about Saturn's moons is that there's this giant subsurface ocean on Enceladus. And not only that, but a lot of this water is kind of being spewed out into space. and ends up being collected around Saturn in this E ring that the Cassini spacecraft discovered. So that's just kind of wild to think that one of Saturn's moons is actually feeding and creating this new ring around Saturn. It also discovered some really interesting dynamics within the rings themselves, including what are called these propeller moonlets, which are essentially just these really, really small moons that are embedded within the rings of Saturn. And as they orbit Saturn, they make these small gaps in the rings, including this sort of like propeller type patterns in the rings itself as it's passing by all of this different material in Saturn's rings. Now, the mission started to come to an end in April of 2017 when Cassini officially began its grand finale part of the mission. It was decided that the Cassini mission would end just because Cassini was running out of fuel at the time. So through all of its life, it sort of burned through the available fuel reserves and it was about to run out. And at that point, NASA essentially had two options. They could either just like let Cassini sort of spin out of control and then have this spacecraft out in orbit around Saturn that they just didn't have any control of. But the risk of doing that is that it could potentially crash into something in the future. The best case scenario would be that it crashed into Saturn itself. But one of the other things it could do is slam right into one of these interesting and dynamic moons like Enceladus or Titan that could potentially have some form of life. So to avoid that potential disaster, what NASA decided to do is just once Cassini was like well and truly out of fuel, they were just going to crash the thing into Saturn's atmosphere. So this had sort of two perks to doing it. One was that you could get a new type of data, essentially, by pushing Cassini so close to Saturn. So you get like a new perspective on the planet and learn more things about Saturn and its ring system just by doing that. But the other perk of that is that it avoids the risk that Cassini is going to crash into something that could have life and potentially disturb anything that had been going on that moon. So in April 2017, it began that grand finale part of the mission where it was a series of 22 orbits that actually took Cassini for the very first time in between the rings of Saturn and Saturn itself. And this was something that they had avoided doing before, partly because it was probably pretty difficult to get Cassini into and out of that orbit, so not really something they want to do. But also because this is kind of like a higher density area of Saturn. So they just wanted to avoid potentially crashing Cassini into maybe some debris or particles from the rings that could have just prematurely ended the spacecraft's life. But since it was about to be decommissioned and crashed into Saturn anyways, there was no reason to not do that. So it had that series of 22 final orbits until September 15th, 2017, where on the final orbit, they just plunged it directly into Saturn's atmosphere. So it was definitely a sad ending to a fantastic mission. It would have been great if that mission had continued. But even though Cassini is no longer existing, it's no longer producing more data. The existing data that it does have it's a ridiculous amount of it. So there are actually still astronomers who use data from Cassini. There is still research being done with archival data from Cassini. So it's still very much alive kind of in that sense. And before I stop talking about Cassini, one interesting piece of Cassini trivia is that the spacecraft is named after the astronomer Giovanni Cassini. It was named after him because he did a lot of research into the Saturn system in around the 1700s, which included discovering 4 of Saturn's moons and also discovering a little gap in the ring system called the Cassini division. Now, one of the cool things, if you come and visit us at the observatory, or we're doing live imaging on the OPV of Saturn, is the telescope here is good enough that you can actually see, you can just see that little Cassini division on Saturn. So this is definitely one more reason to come visit us. But the reason I'm talking about Giovanni Cassini here is because Giovanni Cassini died in 1712 on September 14th, which is one day before when the Cassini spacecraft was plunged into Saturn and the mission ended. So the Cassini mission ended one day after the anniversary of Giovanni Cassini's death. That was not planned at all. That was just kind of an interesting coincidence.
Yeah, I still remember okay, I'm old enough to remember when they put the Huygens lander down and sort of waiting for the mission data and waiting for the mission data because, of course, landing a probe that far away when it takes like hours for the signal to come back was such a, I guess, a risky thing to do at the time, and they were wondering would it work. I mean, like you said, one of the biggest headaches they had was because you couldn't see through. They had no idea what kind of terrain it was going to come down. So they had to
Yeah.
design this lander that could land on a liquid surface, land on a solid surface. So it was a really risky landing because if you do it on Mars or the moon, you actually usually do a fair bit of study ahead of time and find like a very specific landing spot. So this was kind of, dive through the clouds and hope we land somewhere relatively flat because the radar can give you a bit of a sense, but it doesn't have enough detail to know exactly what you're going to
Hmm.
come down on. And when the pictures started coming out, it was like, oh, wow. I'll
Yeah, I
still
mean,
remember that. Yeah.
yeah, those are definitely the most risky types of things to do, but in another sense, they're also the most interesting because it's like, let's just do this and kind of see
Yeah.
what we find. You have no idea what to expect.
Yeah.
Mhm.
And
But
it was such a cool sort of landing because it's like you said, you're in the outer solar system in landing, right? And you're
yeah,
landing on such a cold planet. I mean, you know, and such a thick atmosphere. Like it's not the same as landing on Mars or the moon, where the atmosphere is either much thinner or the moon where you have very little atmosphere at all. This is almost like when they were trying to put stuff down on Venus back in the 1970s and the challenges involved with that. Except in this case, it was really cold,
yeah,
and really, really hot. I mean, it's not nearly as dense an atmosphere as Venus, but still a challenge. But it's like I said, the atmosphere is thick enough that a parachute works really well, which isn't necessarily the case on Mars all the time. Uh,
yeah.
but
And you
yeah,
have to wait so ridiculously long to actually get the data and get the signal back that it happened.
yeah. I mean, you're talking several hours, even when
Yeah.
Saturn's at its closest approach. So,
Mhm.
you're kind of sitting there in mission control going, did everything work? Or have we splattered it across the surface? I mean, that whole mission was fascinating because I remember when they had suspected even before Cassini that Enceladus had something odd coming on, but when they actually got images of the jets and they started to think like, how the heck is something this small active and has water jets coming out the side? I mean, um, you had that happen when you had Galileo and you looked at the moons of Jupiter, and now you were having it happen again with Cassini looking at the moons of Saturn, like how active these bodies were, whereas we tended to think of them as little, dried up lumps of rock where not a lot went on, and yet Enceladus is active and some of the others show evidence of activity. So it was really being up close, you get so much more information. I don't care how good your telescope is, whether it's Hubble or whatever, or really big ground-based telescopes. You just don't get the kind of detail that you do from a space probe. So,
Yeah. This is something that I've mentioned on this show before, and it's going to tie a little bit into what we're talking about later. But there's been so many exoplanets that have been discovered, and I can't help but think like when we have moons in our solar system that are this dynamic and this interesting, you can have so many exoplanets that are so interesting and so weird, but what do their moons look like? Because
mm,
there's got to be moons, if these things exist in our solar system, they got to exist elsewhere too.
yeah, it always makes me think of Endor and Ewoks. I don't know. That's always the image that pops into my head when they start talking about moons, about these extrasolar planets. And, like we're fascinated by Earth-size planets with the extrasolar, but, like some of these Jupiter-sized ones they find, some of them have to have like systems of moons the way the giant planets in our own solar system do, because all four of the giant planets have huge numbers of moons. And
Hmm.
all of them have ones that are, planetary body size, where they're actually big enough to be spherical. So it'll be really interesting to see at what point the telescope technology and everything gets good enough that, if you have a Jupiter-sized planet, can we find this kind of moon system around
Yeah.
one of them? Like that's, I think, the next big discovery in exoplanets is moons
Yeah.
around some of these exoplanets, right?
There was actually, I think it might have been two, but there was definitely at least one proposal last year with James Webb that was looking into discovering exomoons. I have not heard anything about whether or not they were successful or if they published that they weren't successful, but that is potentially in the cards with JWST now.
Yeah, I mean it's got the capabilities to do that. I mean, the trick is though it's not like we have this database of transits where we know there's likely an exoplanet there and you can turn James Webb on it and yes, you will probably see a planet. When you're searching for moons, it's a bit of a crapshoot because you have no other or very little other potential evidence that they might be present, right?
Mhm.
Because we're not good enough to have the techniques or something like a radial velocity curve of a Jupiter to show that it has moons. It's just it's not there yet.
Yeah.
Yet.
Yeah.
Right. It's always yet.
In a future news section, we might talk about it, but
Yeah.
we are reaching the halfway point, so we should probably move on to the next topic,
Yeah.
which you'll be telling us about something really cool.
Yeah, so it's like I said, I've always had sort of a bit of a fascination with the search for extraterrestrial life. I grew up on Star Trek. So in 1959, Cacconi and Morrison, who were into radio astronomy, published an interesting paper, and they published this in Nature, so a very like high level journal. And what it looked at was searching for interstellar communication. So they were really getting into if there is intelligent life out there, how would they communicate and how might we see such a signal? So they talked a lot about like what radio waves you could use, what part of the spectrum might be efficient for a search, and a whole bunch of interesting factors like that. And it was sort of the first, I think, serious scientific paper that looked at this issue of finding extraterrestrial life. Now, in this day and age, we kind of have it in the back of our heads. We've grown up on Star Trek and Star Wars and John Carter of Mars movies and all the sort of, sci-fi. But this was quite radical at the time. And a couple of years later, a fellow by the name of Frank Drake, which if you know anything about the SETI and the search for extraterrestrial life, very famous name, he used sort of the principles in this to do the first real radio searches. He looked at two stars, Epsilon Eridani and Tau Ceti, to see if he could find any of these kind of signals. And this project was called Project Ozma, which again has that literary twist. As Ozma was one of the characters in Frank Baum's oh geez, Dorothy and oh God, why am I brain freezing on this?
Wizard of Oz?
Yes, thank you. Yeah, yeah. The name comes out of his series about the Wizard of Oz. Um, but this was like the first serious one, and Frank Drake was the one who did it. And he and a couple of others are the ones who went on to sort of develop the whole SETI program and sort of the Frank Drake equation. But this was the sort of the major paper that inspired a lot of what he did later on.
Yeah, it's really cool to look at this whole like alien question from the kind of like scientific point of view because there's a whole lot of like sci-fi and everything about it. So it's always interesting to actually see the more like background and sort of sciencey way of you can actually do these like in-depth searches for potential radio signals and potential signatures of intelligent life.
Yeah.
But yeah, I don't know if we will be able to discover alien life, but it's a really interesting thing to think about.
Yeah.
Yeah.
So I think you had a little bit about talking about planets still within our own solar system now.
Yeah, yeah. So this is far back in time again to September 23rd, 1864, which is when the planet Neptune was discovered. Now, the discovery of Neptune is a little bit unique relative to the rest of the planets in our solar system, just because it's not visible to the naked eye, even under the best sky conditions and the best observing conditions. So if you think about the way that all of the other planets in our solar system were discovered, is ancient astronomers would essentially just like look at the sky and watch how things moved throughout the night and over the course of several nights. And they essentially noticed that everything in the sky moves at the same rate, except for a handful of things that they started to call the wanderers. They move at a different pace than the rest of the objects in our solar system, hence the name the wanderers. And the name, the word planet actually comes from that term, the wanderers. So it took a while for people to maybe realize exactly what these wanderers were, but somebody did eventually figure out that these are actually planets in our solar system. But since Neptune is not visible to the naked eye, it couldn't exactly be discovered this way, and you have to use telescopes in order to find it. So you either had to know where it was and do a kind of coordinated search for Neptune to find it, or you had to just essentially get very lucky pointing your telescope at the right part of the sky and notice this thing that essentially just shouldn't be there. But what started happening in 1864 is that there was actually a search conducted specifically looking for this planet that was theoretically predicted to be there, but nobody actually knew about. The idea itself was originally suggested in 1821 by astronomer Alexis Bouvard when he noticed some deviations in the orbit of Uranus, which is the second most distant planet from the Sun after Neptune. When you compared, or when Alexis Bouvard or when other astronomers went and compared the actual position of Uranus in the night sky and also its distance from the sun to what was predicted from Newton's law of gravitation, they started to notice a couple like minor deviations in it, which potentially suggested there could be this other planet in our solar system that nobody really knew about. Now, that solution was one of three other solutions that Alexis Bouvard suggested in 1821, with the other two basically just being that there was some sort of error or problem with the observations or the calculations where everything was okay, but people were just kind of messing up calculations and thinking there was an issue when there wasn't one. Or the other alternative was that gravity does not work the same everywhere in the universe. So when you start to get that far away from the sun, potentially the law of gravitation could change, which led to those deviations and perturbations that they observed in the orbit of Uranus. But I guess that first solution that I mentioned before is probably one of the most exciting ones, which is that there is this undiscovered planet in our solar system. So in 1845, two astronomers, having heard about this problem, started to work on backing out the properties of this potential undiscovered planet from the perturbations observed in the orbit of Uranus. These astronomers were Urbain Le Verrier and John Couch Adams, who were actually working completely independently of each other. They didn't really know that the other person was doing the same kind of work. So they were just they both learned about this and decided to try to figure out the mass of this undiscovered planet and also its position in the sky. And I do also want to point out that this is something that is ridiculously hard to do in 1845. It might be relatively straightforward to do today because we have computers and we can code and have computers do a lot of the work for us. But they were essentially just doing this kind of by hand at the time, where one of the things that they would have to do is make a prediction and then essentially see if the prediction was correct and then make some changes and redo calculations. So this was not an easy thing to do for astronomers at the time and was actually quite complicated. But when these two astronomers started to kind of publish a little bit of their results or discuss these results within the astronomical community, it ended up triggering a bit of a search for this unknown planet. And it turns out that there were two different searches going on at the same time for different astronomers at different observatories searching for these planets. Now, the person that ended up being successful was Jonathan Gottfried Galle, who was the first person to confirm the existence of Neptune. He was working out of the Berlin Observatory using their 9-inch telescope at the time, and he used the predictions based off of Urbain Le Verrier to essentially just point his telescope to the predicted coordinates that Le Verrier had determined for this unknown planet, and essentially just started searching around that area for anything that shouldn't be there. And the way that they did this was literally just by taking a star chart of the area and comparing the positions of the stars in the star chart to what they actually saw on the sky. So this seems like it will be another thing that's a very long and complicated process, but could be done relatively quickly today. But it actually only took him about an hour of searching in that area from Le Verrier's predictions to find Neptune. Over the next couple of nights, he also observed the area again and confirmed the existence of Neptune, this time just based off of more of how the position of Neptune sort of changed relative to the background stars to actually confirm that this was a planet and wasn't just some sort of spurious kind of something else that had popped up, or maybe it was just a star that nobody had noticed before. But anyways, the predictions that these two astronomers had come up with ended up being very accurate, and the confirmed position of Neptune ended up being about a degree away from what was predicted by Le Verrier and 12 degrees away from what was predicted by John Couch Adams. And one other thing I want to point out about this interesting discovery is that although Johann Gottfried Galle was the one to confirm the existence of Neptune, he was actually not the first one to observe it. The first people to observe it were at a different observatory trying to do the same thing. They actually observed Neptune on August 8th and August 12th, but they failed to identify it because the star charts they were using were out of date. So they did see it, but couldn't actually say that this was Neptune because they just didn't fully know it was there, which must have been very annoying to find that out. But actually on September 23rd, 1864, was when Neptune was formally discovered.
Yeah. Well, talking about other people who observed it, what's really interesting is after this, they went back into Galileo's records. And it actually seems like Galileo also observed it, but lost it fairly quickly thereafter, because of course it would be very much at the limits of the kind of equipment he was using.
Really?
Oh yeah, if you sort of look into it, Galileo seems to have observed, I mean, there's no way to tell for sure after the fact, but his observations were consistent where Neptune should have been at the time. So they think Neptune, he actually did catch it on a couple of different nights and then lost it and never sort of went back to it. But he did record where and when he saw it. So, you know,
Yeah.
there's some evidence that actually it was Galileo who first observed it almost 250 years earlier. So it's kind of like one of those, oh, interesting moments. But I mean, Neptune was such a fascinating discovery because it was a case of most discoveries up to that point were just like scanning the sky and you saw it and you mapped it and named it. Whereas Neptune was the first object they really went looking for. Like they had, you know, evidence from the perturbations in Uranus's orbit that there had to be something out there. So they did a calculation and then they went looking for something they suspected was there, rather than the sort of random mapping that a Herschel or a Messier or something had been doing over the last sort of century or so with telescopes. So it was quite interesting that way too. Like it was kind of a turning point in the science of astronomy, of predicting something and then finding it rather than this kind of, you know, general search approach.
Yeah. And I guess a similar thing has been done again in terms of, was it Planet Nine that everybody's been talking about?
Here we go again.
Yeah.
Yeah, it's like this pops up every few years, and then somebody has something that they think, oh, there's more evidence, and it's a brief flurry of activity, and then it kind of disappears again. So,
Yeah. So people, I guess, have searched for Planet Nine quite a few times, but haven't found anything. But
yeah, we
yeah.
found Pluto, but that wasn't it.
Yeah. Yeah. But this is, I guess, sort of our midway point for the show. So, to anybody who's just tuning in, you're listening to York Universe, broadcasting live from the Allan Carswell Observatory at York University in Toronto, Ontario, Canada. You could visit yorku.ca/science/observatory to follow the links to our online chat, where we're posting some live content, or if you have any questions, you could ask it there. Tonight, you're listening to myself, Sana Withers, and Professor Mary Helen Armour. We've been discussing some interesting astronomy history, largely related to solar system and search for extraterrestrial life sort of topics. But we have a couple of reminders before going into our couple of news items. So first up, we have an in-person tour at the observatory on Wednesday, the 24th. This was changed from an atrium tour due to the aforementioned terrible weather that we're getting in Toronto this week. So if you would like to come by and just see the observatory, you could come by on Wednesday, the 24th at what time does it start this week?
It's 7 p.m. this week.
7 p.m., yeah. It is free, but we do ask that you get tickets ahead of time just so that we can control the number of people coming in at the same time. The observatory is a little bit small, so we can't just let a ton of people in all at the same time, which is why we ask for you to get tickets. And the other reminder is just general observing this week. If you are looking to observe something interesting, Saturn and Neptune are both very good targets because they are both at opposition around recently. So Saturn's opposition was actually yesterday on the 21st, and Neptune's opposition is coming up tomorrow on the 23rd. So when I say opposition, I just mean that they're on the opposite side of the sky than the sun. And this is a very good time to observe them because they just look pretty bright in the sky. I know I've been seeing Saturn on a bunch of clear nights. It's always a really fun thing to observe. You can make out the rings even with a small telescope. Neptune is a little bit trickier because it is not visible to the naked eye, but it's still a fun target if you can find it. It has this beautiful little blue color to it. So if you're looking to do some observing this week, Saturn and Neptune should definitely be at the top of your list. But now for some news. We've got two interesting news items, and Mary Helen, you're up first.
Yeah, so NASA is launching another mission tomorrow. This is called the IMAP mission, which is looking at what they call the Interstellar Mapping and Acceleration Probe. And basically what it's looking at is this is looking more at sort of the background magnetic field and solar wind and everything in our solar system. So there is this idea that our solar system is surrounded by something called a heliosphere, which is kind of how far the solar wind extends. So this is kind of looking a combination of the solar wind, some of those magnetic properties, but it'd also be able to study sort of some of the cosmic wind, which is coming from more interstellar space. So it's really looking at this sort of thin material that surrounds us, this sort of bubble of the solar wind and what may be interacting with it. Uh, Interestingly enough, some of our best observations have come from the Voyager probes that were launched decades ago and are now sort of just outside the heliosphere. We got a lot of interesting data as they crossed out that way. This mission is looking at, really what's happening in what we might otherwise term empty space. And what it will also help with, though, is looking at potential sort of solar wind disturbances, because as we rely more and more on satellites and electronics and everything, solar disturbance, becomes a bigger and bigger threat to a whole lot of sort of electronics we use. So this will also have some ability to improve sort of some of the solar wind disturbances and some of the hazards that might be related to it, which is also going to be important if you want to put a colony on the moon, because of course the moon doesn't have an atmosphere, so any of this kind of stuff is going to have a much bigger effect. So this particular probe is aiming to launch tomorrow morning at 7:30 Eastern Daylight Time. Whether the weather will permit it or not, we don't know. Most of these launches have a couple of dates potentially, because if the weather is bad, they can't launch. I don't know quite what it's like down in Florida. So could maybe yes, maybe no. Uh, But it will be very interesting. NASA's website right now is saying weather is 90% favorable for a launch tomorrow, but there are a couple of hurricanes off the coast there, so things could be potentially subject to change in the last few hours. But this is kind of one of those fascinating missions that looking at something that, we've studied a little bit, but not a lot, and yet it potentially could have a lot of effect on us here on Earth. So it's kind of an interesting mission that's going to be launching, and this is tomorrow morning they're aiming for right now. So
Yeah, this is definitely something that needs to be studied a bit more so we don't end up with total chaos. Um, if there's ever any problems with satellites caused by the sun. Um, that really doesn't seem like something I want to deal with.
yeah, but I mean, it's like I said, this is kind of like a project of its time because because we rely on satellites, whether it's for internet or GPS or communication and everything else. SOHO gives us some of those information. There are other solar missions, of course, that are given some of this information, but this is looking more specifically at the solar wind, not the sun itself,
Mhm.
and sort of how far it extends. So it's quite, I think, a timely mission, given, where we are in our use of technology. And thankfully, this one was far enough along that it didn't get scrubbed. And if you've been following the news, there have been some other NASA missions that, haven't fared so well in the last few months. So this one will go. How long they'll support it for, I don't know, but hopefully they at least get the original mission time and get a few years of data out of it.
Mhm.
So
Yeah, this seems really interesting. Because yeah, there really hasn't been something really dedicated to doing this. It's always just been a byproduct of
yeah.
other missions. So yeah, we'll definitely have a lot of cool stuff to come out of that. Yeah. Um, but in terms of the last history item this week, there was an announcement from NASA last week that there have been officially 6,000 exoplanets that have been discovered and whose existence has been confirmed. So before we start talking about the actual discovery of 6,000 exoplanets, let's just take a step back and talk about when the very first exoplanet was discovered, which was, depending on how you define it, was in 1992 or in 1995. The 1992 discovery was a planet that was in orbit around a pulsar. So this is, I guess, could be considered a more exotic exoplanet, would maybe be a good term, because that's a very extreme system and a very extreme location to find an exoplanet. But then a few years later in 1995, the first exoplanet that was orbiting a sun-like star was officially discovered. Now, this discovery was made by astronomers Michael Mayer and Didier Queloz, I think is how you say.
Halos.
Yes, yeah. Well, it was made by those two astronomers, and it was the exoplanet called 51 Pegasi b, which is a gas giant a little bit smaller than Jupiter. And despite the fact that exoplanet science has only really existed for what is that kind of like 30 years now,
Yeah.
so it is a very new type of science, I think. But now, only around 30 years later, there have been officially 6,000 exoplanets that were discovered. Exoplanets in kind of the earlier days were discovered at a little bit of a slower pace. But over the years, as this new subfield has started to get a lot more attention and a lot more recognition for I don't know, discovering exoplanets, there has been a lot more dedicated efforts to searching for exoplanets. This has included various space agencies, including NASA, launching satellites that are specifically dedicated to searching for exoplanets. These are like the Kepler mission, for example, which would just sort of stare at like a large patch of sky over longer periods of time and look for variations in the brightness of stars within that field. So that would be identifying exoplanets using the transit method, where an exoplanet would sort of move in front of its host star and block a little bit of the light from the star and then move away from it. And the brightness of the star would kind of go back up to the original value. So with a lot of these telescopes has come a whole lot of discoveries of exoplanets. So like I said, we're now at officially 6,000 exoplanets, which have been confirmed. But on top of that, there's also a whole bunch more candidate detections of exoplanets, which look like they could be exoplanets, but haven't actually been fully confirmed or sort of met the generally accepted criteria for what a confirmed exoplanet is. So on top of the 6,000 that have been confirmed, there's another 8,000 that are still awaiting confirmation. So we potentially know of even more exoplanets than just the 6,000 that have been confirmed. So the press release from NASA did sort of mention that it's kind of hard to give one exoplanet the designation of being the 6,000th exoplanet discovered, just because of how the discoveries of exoplanets are actually reported. But the one that they do highlight, and I guess the closest thing to the 6,000th exoplanet would be this thing with a super long and ridiculous name called KMT-2023-BLG 1896LB, with the B actually being the name for the exoplanet and the rest of that whole string of nonsense being the name of the star. This exoplanet is a Neptune-like planet that's orbiting a star around 18,000 light years away from the Earth. So Neptune-like planets are essentially planets that have atmospheres and structures very similar to the planets Uranus and Neptune. So they have these massive atmospheres that are made up of primarily hydrogen and helium, but then they actually have these cores that are made of sort of more solid rock and metals. And when I say metals, I'm referring to the astronomer definition of what a metal is, which is anything that's heavier than hydrogen or helium. But in total, it's around 16 times as massive as the Earth, and it orbits around 2.8 astronomical units from its host star. So that seems kind of weird to me a little bit because Neptune orbits much, much further away from the sun than this exoplanet does. So in other systems, it is possible to have these weird combinations of these really massive exoplanets that are actually orbiting very close to its host star. Now, breaking down the numbers of exoplanets that have been discovered, of the 6,000 of them that are confirmed, there's around 2,000 that are like Neptune and Uranus, so like the one that I mentioned before. Around another 2,000 are more similar to Jupiter, and this is both in terms of their composition and of their mass. Then there's around 1,700 that are what are referred to as super-Earths, which are kind of rocky planets that are larger than the Earth, but then also not as massive as the gas giants like Neptune or Saturn or Jupiter. And then finally, there's another 700 planets that are kind of the rocky and terrestrial type of planets. So while those are kind of the few main categories that you can classify exoplanets into, there's a whole lot of other weird things that exoplanets can do. So we are talking about some of the really interesting moons in our solar system. When you go to other solar systems, it turns out that their exoplanets can also be these really interesting and dynamic systems that are things like directly out of science fiction. One of those are lava planets. Which are actually like the planet Mustafar in Star Wars, where you literally have like lava on these exoplanets just because it's so crazy hot orbiting close to its host star. You also have a couple of other weird exoplanets, like exoplanets that rain glass. There's an exoplanet that is this giant gas giant planet, but orbiting really, really close to its host star. So close to it, its atmosphere is just constantly evaporating, and there's a lot of mass that's constantly being boiled off of the atmosphere of this planet and into its host star. You even have exoplanets that are called rogue planets that don't actually orbit any star. So these are planets that were formed in a solar system and then for one reason or another just got booted out of their solar system and are now essentially just wandering the galaxy all by themselves. And these can be kind of tricky to identify, but there are actually large numbers of these rogue planets that have been identified within the Milky Way. So kind of tying back to a little bit of what I said before about how many exoplanets are being discovered over time. The discovery rate of exoplanets is pretty much increasing exponentially at this point. Last year, there were only 5,000 confirmed exoplanets. And then, which means in the past year, astronomers have discovered another 1,000 exoplanets. So the rate at which exoplanets are being discovered is, quickly increasing. And this is especially going to be true within the next few years when other telescopes start to come online, which can really help with the search for exoplanets. This includes the Roman Space Telescope, which is going to be doing a whole bunch of different things. But one of the things it's going to be doing is searching for exoplanets using some of its surveys. It's also going to have the most advanced coronagraph that has ever been put into space on it. And this is just an instrument that astronomers use to actually get direct images of exoplanets. So it's going to really open up the kind of exoplanets that can be directly observed through coronagraphy. So these are really not exoplanets that we're able to observe this way from the ground or with other space telescopes, even with James Webb. So it's going to do a whole lot for exoplanet science, and lots of cool things are going to come out of that. So it's a great milestone to pass, and we'll definitely have more interesting exoplanet science coming out of existing data and from upcoming telescopes.
Yeah. I mean, I remember like when the sort of just doing my master's in sort of late 90s, early 2000 when, the whole exoplanet thing was just getting going. And, at first in the sort of mid to late 90s, early 2000s, you were talking about, a few tens, a few dozens of these exoplanets because they had to find them all individually through sort of the radial method, like using Doppler shifts was the thing at first. And then Kepler came along and
Yeah.
it just exponentially changed it. I mean, Kepler was sort of successful, I think, beyond anybody's wildest dreams. And the sheer number of um, potential planets it found was phenomenal. Now, they had to be confirmed by another method usually, but Kepler was the real game changer, right? I mean, before that, you had to sort of look at individual stars and observe individual stars and look for particular characteristics. And then along comes Kepler that could look at like 100,000 stars at a time to try and find it. So it's just phenomenal. And they had so much data. They actually were running sort of online planet hunting where you could download the data and search for transits because they just had so much data. They didn't know what to do with it. I think some of the variable star people benefited from the Kepler mission too, because of course it was observing so many stars for so long. You had this massive database of stellar brightnesses, so it was one of those side benefits of the mission. But it was Kepler that got it going, and then of course Tess came along, and that's it. It sort of changed the whole game, sort of between around sort of 2008, 2010, 2012, when Kepler really started going and dumping all this data down. So I
Yeah.
don't remember the exact year Kepler launched, but it was in that sort of time period. But I remember following Kepler from the time it was like a discovery mission proposal to sort of launch and then sort of success. It was really kind of cool.
Uh, we have actually used data from tests at the observatory for XXIG, because a couple of the variable stars that we look at with the 60 centimeter ended up being in that test footprint. So the last paper that the observatory published on XXIG a few years ago used some test data for Fourier analysis. So it's definitely useful to a lot of astronomers.
Yeah, I mean, the sheer amount of data those missions collected, like they're still digging through it for, stuff. And it's like I said, observe so many stars that if you're looking for something, it's like, well, check the data. There might be something there. But it's such a I mean, but this is where AI could come in and help, like, okay, well, here are the basic characteristics of a transit. See if you can find me how many are there, rather than having, 1,000 people sitting at home in their laptops looking for transits and endless sort of um, brightness data from stars, which can get rather tedious. Yeah.
Yeah.
But I
I
did it. I did it when the Kepler mission was out. I was one of those ones who downloaded and sort of searched for transits and marked stuff, and it was just like it was kind of cool.
Yeah, it's a lot of fun to be able to just kind of play around with data like that. I love sort of just messing around with large data sets and looking for interesting and weird things. So that's definitely like probably something I would have done. Yeah. But that is also one of the great things about really large data sets that comes out of these telescopes is like, even once the mission is done, it's still going to be giving you amazing science for years to come.
Yeah. I mean, they're still digging stuff out of the Cassini mission. They're still digging stuff out of the Galileo mission because there's just so much data, and they just, you put it somewhere, and it's like, okay, like here it is. If you want to just come and get it, because we don't know what to do with it.
Yeah. Yeah, and that's one of the things with the Roman space telescope that I mentioned is like the volume of data that this telescope is going to be using is like they have to kind of almost build new like systems to just handle that. And
Yeah.
it's not just Roman, it's also the Vera Rubin Observatory in Chile.
Yeah.
Like the all sky surveys that thing is doing is just it's producing an unimaginable amount
Yeah.
of data.
Yeah, I mean, even with the Kepler mission, when they were planning it, they had the same problem. I mean, this is sort of like late 90s, early 2000s when you're planning it, but they're like, oh my God, we're going to get so much data. How do we actually download it all off the space probe down into our Earth-based computers, right? Because it was just like,
Yeah.
oh my God, what do we do with all this data? So it was part of the mission to even figure out how to get it back to Earth. So,
Yeah, but it's always worth it for how much cool science comes out of it. Um, but that is the end of our show today. So, everyone, you have been listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Professor Mary Helen Armour and myself, Sana Withers. You can always connect with us on Instagram at the handle at York U Observatory and on Facebook at Allan I Carswell Obs. You can also check out our websites for show notes, content updates, and contact info at yorku.ca/science/observatory. Thanks for tuning in, clear skies, and have a good night.